What you just saw is a computer vision-based system that tracks a player's speed in real time, without any wearables or specialized sensors. Just a camera and advanced AI algorithms. This is the power of computer vision in sports analytics. Traditionally, analyzing player performance required manual effort, expensive equipment, or complex setups. But with computer vision, we can extract meaningful insights, such as speed, agility, and movement patterns, directly from video footage. For the sports industry, the impact is massive. Coaches and analysts gain objective, data-driven performance metrics. Athletes get deeper insights to optimize training. Broadcasters can enrich fan experiences with live, interactive statistics. In short, computer vision is reshaping sports analytics, and in this tutorial we are going to learn how you can find the simple analytics like speed of a player using computer vision.
Hello guys, welcome to another computer vision tutorial. So as you've seen our intro, in this tutorial we are going to learn how you can use YOLO for finding an athlete speed using computer vision. So to do that, you just have to follow some simple steps. So let's do this. Our first step is dataset creation and annotation. So we need to create a dataset on which we will train our YOLO model. So for this tutorial, I have selected this video as a reference. As you can see, it's a tennis match between two players. So our task is to find the speed of these two players. So to do that, I have to extract some frames from this video and annotate it and use that annotated data to train our YOLO model. I have created a Git repo to simplify our process of data creation. So as you can see, this Git repo has been cloned. Using that Git repo, you can extract frames at random from that tennis match video. As you can see, I am extracting total 20 images. Let's extract it. As you can see, 20 random images from our video has been extracted. Now we just have to annotate these data set on the classes of uh, athlete. So to do that, you can use our labeler platform. So let's go to our labeler platform and upload these images. As you can see now, in our next step, I have uploaded our data set on labeler platform and created a class called tennis player. So using labeler, I can annotate it with bounding boxes. As you can see, I have to annotate these two objects, which are tennis player, which I have to detect. And as you can see, two annotation has been done. We have to just submit it and extract our annotation in CocoJSON format at the end when all the data set has been annotated. So let's get to our next step of converting our CocoJSON to YOLO format. So when your annotation will be completed on the data set, you have to export it into CocoJSON format. It will look something like this. Now, our next task is to convert that CocoJSON, which is this, into YOLO format. So to do that, you have to just use our Git repo to convert into Coco to YOLO converter. So you have to import from bounding box converter Coco to YOLO converter function and provide it with JSON part, image directory with the data set, and the output directory name. Let's run this. As you can see, our data set has been converted into YOLO format, which has two directories, images and label. So let's get to our next step of model training using this annotation data. In our next step, we have to fine tune YOLO on our custom data set. To do that, you have to import some libraries. From Ultralytics, you have to import YOLO, which is must. And then you have to use this command line. This command line help you fine tune YOLO on your own custom dataset. So it includes YOLO 10 task equals to detect, mode equals to train, and data, which is part to dataset.ym. When you create when you create YOLO format, it have a dataset.yml. You have to provide the parts to this here. As you can see, this is, and then the model name, and then the number of epochs you want to train on, and the image size and the batch size. Let's run this and let's wait and see the result. So when the training is completed, you will see there is a runs folder created, and inside runs folder there is detect and train. So in that weights folder, there is your model in .pt format. Now our next step is to see the model inference and how it performed on our video. Let's get to our next step. To see the model inference, we are going to use that video and then extract a frame from that video and see the model inference result. So let's provide the path to the video. I am going to use and extract a frame. You can use it using the OpenCV library. So let's see what happened here. Now let's run this. As you can see, a single frame has been extracted from our video. It's a 50th frame of our video. Let's see the model inference result. You just have to use YOLO and provide the path to the model weights and use model.track, and the source is the frame, which is this I have provided into variable frame. As you can see, it has tracked our both tennis player ID1 and ID2. So let's get to our next step of drawing the boundary of this tennis ground to perform speed estimation of the player. To extract the boundary of the tennis ground, I have created a simple function which helps us to extract the edge corners of the background. So let's run this. As you can see, when it run this code, it appears a screen of, and it has a frame of the video. So you just have to click the edge corners of that ground to extract its value. Now, as you can see, I have pointed out the corners of the tennis ground. Let's press escape. As you can see, our value of corners has been stored in a list, and you just have to insert provide that list to our plane coordinate. Similarly, you can also extract the values of the net. So I have already done that. Let's see the result here. So let's mm, so as you can see, these are the corner edges of the ground, and this green is the net which divides the middle. So let's get to our next step of converting these data into computer vision logic to find the speed of these two tennis players. Let's get to our next step. So in this step, we are going to see how computer vision help us in finding the speed of the athlete. So to do that, you have to find some real world constants like the length of the court and the width of the court. I am using the international standard for that. And then you have to find the corner point of the court, which I have done in previous step. So with this, you have find some absolute values. Let's run this. Now, in our next step, I have created a class which have several functions which help us in finding the speed of the athlete. So I initialize the class with the model part, the FPS of the video, the position of the player, which contain the center point X and Y, and the time in which the model uh, inference the position of the athlete and the current speed, which is stored in these dictionary. And then there is two variables called pixel to meter ratio and perspective matrix. Let's find out what these are. As you can see, this function set code calibration is help us in setting the perspective matrix here. So what is perspective matrix? Let's see this frame. As you can see, the code look like a trapezium, means this side is longer than this side. So in normal computer vision, we use the movement of pixel from previous frame to next frame to see how this much distance it has covered, and then find using time at which inference happen to find the speed of the object. Speed equals to distance by time. So the distance we get using pixel and time we get using inference. So if our object covered this here, covered this distance, it will cover longer distance in smaller time, in equal time than this object, as it is further away from us. So we use perspective transformation to convert this plane into a rectangle for both object to have equal distance to travel at equal inference rate. So it will convert our trapezium into a rectangle. So this is the minimalistic information you need to know about uh, perspective transformation. You just have to provide the coordinates of the top width, bottom width, left height, and right height of the code plane, and then using the OpenCV OpenCV function get perspective transfer, it will convert it. You also have to provide the DST corner. DST corner is the points of a rectangle you want to convert it. So I am using a rectangle with length 600 meter, 600 pixel, and a breadth 150 uh, pixel. So that means I'm converting this into a rectangle of 600 by 150. So with this, our this function is complete. Let's get to our next step. So this perform the that same thing, but apply perspective correction to the point. It also means it just like plane, it also needed for the point. It will just do that, and then we use calculate speed. We first use the track ID and the position which we have stored in the position variable. With track ID, we are going to track object of, and then using simple maths of previous position in previous frame with next position in next frame, we will find the distance. We will find the ratio of how much pixel is equal to how much meter using the value which we have given, that if the pixel length of this value is 100 and the value of this width is 100 meters, that means 1 pixel equals 1 meter. So using that logic, we will find the speed, and then our next step, we will process the frame using our model and track each object and then annotate that object. It's simple as that. I have seen it done it various time. And then we use a draw speed display. It helps us to draw the value which we get from the from performing this function, which is speed, and showing up on the screen. So with this, our classes function has been done. So let's run this. This is a simple function which help us to perform the speed estimation on video. frame by frame. So it's just process the frame and passes to the process frame function which we have created. So let's run this now. We just have to use the run real-time speed tracking and provide with model part and the video part and the model part, which are these two variables. Let's run this and see the result. As you see in the result, it works greatly. We need some more calibration to find the exact speed of the athlete to the more accurate value. So to do that, you have to find a real world constant first. So as you can see, the code calibrated value of ratio means the ratio between the actual rent and the pixel is around 0.0235. The more accurate value we got of this, the more actual speed we will get of the athlete. So with this, you know how you can find the speed of the athlete using computer vision. Let's see you on our next computer vision tutorial.
For more computer vision or machine learning related tasks, you can check our GitHub, where you will find everything in one place.